about those things, but basically I'm standing on behalf of Rodrigo, who was announced as the presenter, but he had some personal issues a couple of days ago, and he asked me to present. So, very short notice, I sorted things out, and I hope I don't disappoint you. But I'll go forward with today's presentation. Just really let me organize here. So. Let's see. I suppose you're seeing my full screen now.
Yes, we are.
All right. So hello everyone. Good morning, good afternoon, good evening. So as I said, I'm Luis Marcelo Tavares. I'm the head of the Laboratory of Immunotechnology, which is one of the institutes of the GCC at University of Rio de Janeiro in Brazil. And I'm speaking here on behalf, in particular, of Rodrigo Carvalho, who is one of the newest members of the GCC. He's a colleague of mine, but also to from on behalf of Alessandro, who was the PhD student, now a doctor on this topic, and Dr. Horacio Petit as well, who is working with us exactly on this topic. And the topic today of the GCC seminar will be modeling of vertical stir milling with the UFRJ mechanistic approach. So the outline of my talk today, after a brief introduction, I'll show exactly the scope of the work that we have done, and then move on to talk about some briefly on the mechanistic model that we have been working on for a number of years now, and quickly move on to applications on determining how this model was modified, adapted to describe batch milling, and then to continuous vertical stir milling, and move on to the conclusions and some of the ongoing work that we are doing as well. Well, I think there's a little doubt if you look at the amount of horsepower and power mills operating in industry, in the mining industry these days, and you can see definitely ball mills and autogenous, semi-autogenous mills, and even rod mills make up for most of the work that we do in size reduction. But when we look at the fine and ultra-fine size ranges, especially on regrinding, we're quite happy to see that these mills are being challenged by other technologies. And one of the technologies that have been really well studied these last few years is obviously steel milling. And you can see here, for instance, from this graph that Matzo really publicizes a lot on the benefit of stir milling, that if you look at the energy versus P80 curve, over a range of coarse grinding to regrinding and fine and ultrafine grinding, it really shows, as we know, that the amount of energy increases quite dramatically as the product size decreases. But that drop, that increase is not as sharp when you look at stir milling, uh, pretty much showing that if you're actually doing coarse grinding, you're still well off using conventional tumbling mills. But as you move on, typically below 100 microns, you potentially benefit more and more from used stir milling technology. And I think there's plenty of good evidence that if you go well into the ultra-fine size range, of the huge benefit of the stir milling. And when you're talking about this regrinding range or fine grinding, of course, we tend to look at the vertical stir mills as the ones that are really most used in industry these days. I think it's interesting to really look quickly at these vertical stir mills as far as which would be the key advantage of this technology compared to ball mills. I think the energy intensity has been demonstrated, even though these are not yet really high intensity mills because of the relatively low tip velocities of the screws. Their intensity in terms of volume is higher than we have in ball mills, which is really beneficial when we talk about finer grinding. And of course, as I showed in the previous slide, they tend to be more energy efficient than ball mills, also being attractive. I think the challenges that we have, because we have been accustomed to using larger and larger ball mills with larger and larger powers in the tens and 20 megawatt powers, we are not yet there in the case of vertical stir mills, and it really creates a potential for development in the future, at least for the mining industry. And really talking about exactly these vertical stir mills, we know that First designs were from the 1950s from Japan's Kubota mill, but they really became quite popular, and they are right now in their versions, particularly the Verde mill from Metso and the Tower mill from Irish. And basically, these mills are very similar as far as design, characteristics, applications, and so on. And I guess really, as I mentioned before, is likely still limited as far as maximum power and therefore capacity, really still showing the benefit that it can be having in the future. This is just a picture of a setup here in Brazil where they have 8 of these stud mills operating for final grinding of iron ore. So when we look at the stir milling technology, even only vertical stir mills, we have seen a lot of developments these last few years. And some of the designs, for instance, that we have seen a lot of advances in the mining industry include the SMD from Metso, the HIC mill, formerly from Mototech, now from Metso, but also STM, VXP mill, those are basically slightly different designs and different concepts, but still of the same potential system and technology. So if I were really, and we very often are working with the mining industry, and we're in a position that we want to select what is the best technology for a given application, or even in the case that you already purchased the mill and you're wondering what is the optimal operating conditions that you should be looking at, it's not a straightforward task, I'd say, because of the many operating variables, as well as the several design variables. So that's basically the motivation to use the state-of-the-art mathematical models to help us understand that. Because uh, with the variety of operating and design conditions, it's not easy for people to basically test physically on every one of them. And there's obviously the challenge of scaling up. What you test in the small scale, how much can you really trust that it's going to be exactly like that in the really industrial scale? So this really brings us to the scope of today's presentation, which is, and the work that we have been doing now for a number of years, which is to develop a mechanistic model for grinding and apply it for vertical stirred mills that would account for basically all important design variables in the mill and all important operating variables in that type of mill, seeking to predict essentially the mill power and obviously the product size distribution, which is the key outcome in comminution. So in order to do that, we use what we call the UFRJ mechanistic mill model, which is essentially a multi-scale modeling approach that really tries to do as much as possible to decouple the contributions from the feed, the ore, from the milling environment. And how do you do that? Just really very briefly, what we do is use the discrete element method, which is a very powerful simulation tool to understand what happens inside the mill as far as the collision energy spectrum, that is, energies and frequencies of collisions, as really the basis for understanding what's going to happen inside the size reduction process. On the other hand, we need to understand how particles will respond to those collisions, and this is really described by a number of models at the microscale level of every single collision event. We have to acknowledge that in these mills, very likely particles will be stressed in the form of beds, can be even monolayer beds, but that is important to understand. So using these three pieces of information, we can really predict what happens in the real world, which is the product size, the throughput, and of course, power and so on. And what we do to be able to do that is a special formulation of population balance model and what we have called the fracture energy convolution, which is to acknowledge the fact that particles don't really have exactly the same strength. They have a variability in their strength, and they tend to survive when they're tougher, and they tend to weaken when they really receive repeated collision events. So I won't go into the math here because it's really very early at this time in Brazil, but really the phenomenology behind this has been all described in all of these papers you can see. And the idea is that originally this model, a number of years ago, has been proposed for tumbling mills. And we have used it for ball mills, we have used it for autogenous and semi-autogenous mills. But the idea behind the model, without putting equations here, is to really be able to analyze the outcome of every collision event in the mill. So using this picture here, imagine that these are two grinding medium colliding against each other in any type of mill. The idea of the model is that it accounts for the fact that some particles will be in the collision course of these balls, so will be involved in the event. Some particles will not be involved because they're just likelihood of being captured. So a part is not captured, so nothing happens with that small fraction of the population. Those particles that are captured, there is a chance that some of them may not receive enough energy, so they don't really get fractured, but they might really lose some fine debris because of the low energy involved in the collision, and they may also have their strength reduced by damage, and this is already accounted for. Of course, some of the particles which are really right on the track of the collision and really are stressed with high energy may be fractured, and there's still a chance that they may remain in the same size range or they may become finer with the debris. And these are all described what we call body breakage, which is energy dependent, depending on the stressing energies involved in the collision. And all of these result in mass balances for each event and result in how particles change their strength. Sometimes they don't, sometimes they become weaker, sometimes they just break and disappear from that class. So this is exactly the underlying understanding from the model that is really captured in all integral differential equations, which are pretty complex, but today we can really solve them numerically quite easily. And so, what is behind this model as far as the breakage distribution? This is, in my opinion, a very important differential of our approach because we account, for instance, for a number of important things that characterize the response of particles. For instance, we understand that for every particle size, there is a variability in the particle strength. Even particles of the same composition, the same material, they really have a variety of particle strengths, which is illustrated in this graph, for instance, that a given size and a given material, there are particles that require as little as 20 kilowatt hours, joules per kilogram to break. And in the same batch, there are particles that require 300 joules per kilogram. And so this variability is accounted for in the model, and it's described by this log normal distribution, opportunity. The other part of the model is that, of course, this variability varies as a function of size. And we have this model here, which is really described as a function of using reliability theory that accounts for the fact that the strength of particles changes as a function of particle size. We have known for a long time that very coarse particles tend to be more brittle, easier to break, whereas as particle size is reduced, they become tougher. And this is represented by this model. The third part of the model here is what we call the damage mechanics model of particle breakage, which accounts for the accumulation of damage when particles receive repeated impacts. So, for instance, when you stress particles one by one a number of times, the first time, second, third, and fourth, and so on, you can see quite clearly that as you stress over and over again, more and more particles will break. And this line here is described exactly by this equation, which has only one fitting parameter. And the other part of the body breakage distribution or volume breakage is the extent of breakage, how much breakage occurred as a result of that event. And that is described using an improvement and a modification of the T10 procedure, which accounts for the stressing energy in that collision event and also how much fracture energy those particles that the stressing event had. So this is typically what we do in the lab. So we test particles over a range of sizes, and we fit this line here, which is exactly this equation here. And this, a very last part of the model is the mass loss due to surface breakage. And you know that there's that surface breakage event, a little bit of mass loss, but a number of events can be quite significant. So we have used this model, which is based on a model that was proposed by Gadidi and Zhang from Leeds. And essentially, this model accounts for the fact that as particles receive more and more energy, a little bit more and more debris will be lost from their surface. And the key thing is that all of these models have been proposed quite a number of years ago, actually, from my PhD thesis, nearly 30 years ago now, and we have published this widely and validated. So this is the engine in the back. But now when we look at stirred mills, how do we use this understanding that there's much more happening than just breakage? There's transport inside the mill, there's classification. And this is the vision that we have put together to describe what happens in real continuous vertical stirred mills as we have in industry. In the left side of the graph is exactly what I just showed, which is the particle characteristics, which include the particle contact parameters, of course, the material contact parameters in the EM, the rheological properties, the breakage properties as far as body and surface breakage, as well as, of course, the size distribution. And on the other hand, we know that we need to account for the equipment design and operating conditions, and we do that by influencing the parameters that are really being used in the DEM simulation to describe media motion, the CFD simulation to describe the fluid flow inside, in between the grinding media, and this DPN is the discrete particle or phase model, which is essentially a model that allows us to use tracers to understand how particles will respond
I
inside
couldn't
the.
see that
And
PowerPoint.
so this is essentially this is the background tools that we use together with this information from the particles to be able to account for a number of things, which is slurry and grinding immediate motion, collision energy, the mixing description, and the partition in the case of classification. Now, all of this piece of information go into this population balance model that I just mentioned, which is called a UFRJ mechanistic model. And the outcomes is exactly the particle size distribution of the product and the strengths of the particles that are still surviving after each event. So this is essentially the structure of the model. And what I'll be able to show you now is how we have demonstrated its validity, first in batch operation. So we used data from a PhD thesis from a number of years ago. Malcolm supervised it from Hassan at the University of Queensland. And this is the mill he used. It's basically a mill that uses a screw, like typically vertical stirred mills, a bench scale, and he did quite a few experiments changing ore type, ball size, solids concentration, rotational velocity. And those tests were done with a fixed grinding time of 2 minutes. So we got the data very nicely from them, and we're able to now use the simulation approach to verify, can we predict or validate our model using those data? So this is just an illustration of that small mill, showing here the grinding media motion. And what we have done in this first work that is published here is we just simulated using DEM. We didn't account for the fluid here because we really were testing with very coarse grinding media, like 20 millimeter balls. We assumed that this volume was perfectly mixed, and we propose one definition of effective collision energy, which is every collision that happens in the mill will influence breakage, accounting for the normal direction of the collision will be fully used in breakage, and only a fraction of the shear energy will contribute to breakage. And that fraction is a function of this K value, and this K value we have found to be dependent of the percent solids in the slurry. So the first thing, as I mentioned, that we can use using DEM is to predict the power in the mill. So you can see here quite a few tests were done, and he measured the power in that small mill. And we could compare quite favorably with our predictions using DEM, even for different grinding ball sizes. The other important thing that we use in the simulation is the fracture energies and the strength. Remember that a function that I showed before, which is the variation of the fracture energies as a function of size. And we actually use real measurements from single particle breakage tests. You can see here particles as coarse as 30 millimeters to for particles as fine as 200 microns. And that work was done by Malcolm and his team. And we got the data here to be able to fit our model to all of this data, showing the typical effect of as particles reduce in size, their strength increases. So we could get real direct particle breakage information here to be able to put together in the model. Well, and then to be able to validate the model, basically, we predicted the lines here are predictions using the population balance approach, whereas the dots, the points here are basically the experiments that were done over a range of percent solids, over a range of tip speeds. And you can see the fit is quite good without fitting any additional parameters from each simulation. In the case of limestone, that the size distribution was slightly coarser, pretty much the same thing. The predictions for different percent solids and different tip speeds agreed quite well with the data. With the only thing that in the case of limestone, we didn't have breakage data as we had for copper ore. So we had one of the tests that were used for model fitting to back calculate breakage parameters, which is not ideal, but appeared to be a valid approach in this case. But the problem with this test that they conducted is that they changed it more than one variable at a time. So sometimes it was not easy to understand the effect of one variable against the other because sometimes two of them were varied together. So we decided to do a simulation sensitivity analysis just to really check if our perception of predictions from the model and our experience would actually agree by using simulation. So to be able to calculate the breakage rates, remember that our model is not based on breakage rates. We predict size distribution of the product. But it was really an interesting thing to be able, would we be able to predict breakage rates in a way that we could compare to our experience practical one, for instance? We basically did these simulations for different narrow size particles here from 0.15 to zero point 0.1 to as coarse as 4 millimeters. And we predicted in the simulations how much material is still surviving in those size classes. As you know from comminution, I'm assuming that all material was in that narrow size range. As time progresses, less and less material will survive. In the case of very fine particles, given their low likelihood of being nipped by the grinding media, the breakage rates were relatively low because particles, they escaped from the collisions, whereas in the case of coarse particles, they're fairly high because cannot escape as readily. The rates here are relatively linear, so they show that the assumption that we usually use of linearity of breakage rates holds for some sizes, doesn't really hold for very coarse sizes because of the effect that we have seen before. The coarse particles are so coarse that really they can sometimes survive breakage events and still remain inside the mill. So all of these were predictions. So from these lines, we got the slopes, which is basically the breakage rates, and plotted now as a function of particle size. And the result is the picture on the left that we can see something quite familiar to what we know, which is how the breakage rates change with size, which is exactly the same in the left. Very fine particles, breakage rates fairly low. As sizes increase, breakage rates increase, and if you increase too much, breakage rates start to drop, which results in an accumulation of that coarse sand inside the mill. For softer limestone, pretty much the same trend under the same conditions, just really higher rates because of the lower the strength. Now that we look at let's look at other variables, how they influence. For instance, tip speed is a classical variable in stirred milling. So we wanted to see how variations from 1 to 4 meters per second would influence breakage rates. Quite dramatic effect here. For 1 meter per second, very, very little grinding rates. And the reason, as you can see here on the left, very low collision frequencies and even very low energies, almost too low to justify grinding using this large mill. But as you actually go to higher speeds, there's a jump from 1 to 2 and then so on. because exactly of the massive increase in the frequency of collisions and going to also higher collision energies. And you can see it's just a shift of the breakage rates curve to higher values and a slight change here in the ability to grind coarser particles. So this is all predicted in the model. But the nice thing is those not obvious effects. For instance, what is the effect of solids concentration? Hassan in his work has shown that there's a benefit to use lower percent solids here by really higher breakage rates for coarse particles. But we can see here there's a little bit of a loss or similar for finer for coarser particles. Whereas for very high concentrations, there is a drop here in the breakage rates. But of course, bear in mind that the amount of material increases when you increase the percent solids. So in the fine, the net effect ends up being quite beneficial for using higher percent solids in size reduction. But also one important effect that we have known for a long time is the effect of ball size. And you can see here, for instance, if you use very large ball sizes, here 27 millimeters, you sacrifice grinding of the fine particles. You have lower breakage rates of the fine particles, but you benefit from being able to break very coarse particles here. On the other hand, if you go to very small grinding media, like 15 millimeters for this type of mill, you benefit quite a bit in the fine size range, but you sacrifice grinding coarse. So you should as well really be careful of not feeding coarse particles with small grinding media. We have known all of this, but here we can predict exactly how these curves change. Well, one very unusual effect that we have seen in vertical stirred milling is the fact that the screw doesn't really wear evenly. So when you start a new screw in your mill, it looks like this, but after a while of operation, actually it starts to uh, reduce in diameter in the below and on the top pretty much remaining the same. And what people have done in practice, of course, before changing the screw surfacing is really to deal with this and understand how to keep steel grinding fine. So here is interesting to see that when you have a new screw in this small mill, this is exactly how it looks like. But as you actually start to wear, first, there is a larger volume available of material. So if you keep the same volume of balls, there's a slight reduction in overall volume here. And what we have done in the simulation is done exactly how they have done in industry, which is to compensate the wear by increasing the volume of balls and wanted to see how the impact that really resulted in the grinding result. So what you can see here is the breakage rates here is that the blue line shows exactly the new screw, which is definitely much higher breakage rates. If you could have a screw like that forever, it would be fantastic because that's exactly the ideal condition. And what you can see here, if you don't change the amount of grinding media, as you wear almost to the bone here, you see quite a dramatic drop in the grinding ability with the red line. And what we have seen in practice is that those guys in industry, they increase the amount of balls to compensate for that. But that only really compensates partially for this effect. So it doesn't really go back to the new, but at least it's not as bad as the red line, keeping the same volume of balls. So all of these things are not easy to see in practice because of the fluctuations and the difficulties, but we have been able to see through simulation. So just a final, like a psychedelic type of simulation, because what happens if you change completely the ratio between the screw and the mill diameter? What we have seen in practice, what we have done in practice, the simulation, the base case from Hassan was this middle one, 1.9 ratio. But what if we strangulate this, we use a smaller vessel here, or we use an oversized vessel? What happens? Well, the simulations are quite obvious that if you use a very large vessel, a lot of dead volumes here, a lot of grinding media barely moving. Whereas if you use a small diameter, there's a lot of action. Almost everything is in motion. So we wanted to see the impact of this on product size and breakage rates. It's quite obvious that if you go to the very large ratios, everything drops. The energies drops, the frequencies drop. But it's interesting to see that if you strangulate the mill here, also the frequency drops in collisions, even though, of course, the median collision energy increases. But when you see here the curves, it really is, it shows that indeed for a small ratio, 1.6, there's the highest breakage rates. There's a little bit of drop here in the 1.9 case, which is the typical case, and quite a massive one for much larger mill diameter. So this drop typically is more than compensated by increasing volume, active volume of grinding media, and of course of slurry that you put in the mill. So all of those things we have been able to predict with our numerical model. So just the final part of the presentation today, of course, I think that we're more excited about is to go to real continuous mills. And continuous grinding, there had been a few nice studies in the literature. We selected the work from Alex Yankovic from the JK, actually from the thesis at the JK a number of years ago. He actually got this mill, a pilot scale mill in this system here, where he actually used the mill in multiple passes, so with two tanks. So he could actually simulate continuous operation as in multiple passes, for instance, by feeding from one tank and then discharging to the next, and then doing the same over and over again to be able to simulate several stages in series. It is, well, it was basically a continuous operation with multiple passes using different grinding media sizes with a mill of about 5 kilowatt power. And the feed was calcite. So all the geometry, it's a fairly large pilot scale mill, 1.1 meter height. So how did we go about modeling this mill? So to model, we understood that the mill is essentially composed of two major grinding in two different zones. One is the top zone, where there's potential classification, because remember that the feed comes from the bottom, the slurry, and out it comes out from the top. So in the very top of the mill, there's a potential of really coarse particles dropping back into the grinding zone. And this is described using coupling of the discrete element method, computational fluid dynamics, and this DPM tool. On the other hand, in this grinding zone here, which we actually described using a number of mixers in series, because the slurry comes from the bottom and comes out of the top, we use the coupling of DEM with CFD and use our population balance model, which is the mechanistic UFRJ model, to describe it. Well, so let's go and talk about each of them. Let's first look at the classification zone using these coupling of tools. The way we dealt with this is by considering a uniform particle size distribution for this injection of these tracers here inside the CFD simulation. And those DPN particles were anywhere from 1 micron to 1,000 millimeter, 1,000 microns, just for the sake of building a partition curve. So there's all the modeling background from that. So the drag and the added mass force was considered. The Gedaspo model was used for the CFD, and we used fairly long times to be able to still get a steady state result out of this. We just did a few case studies, and essentially we only, to make simulations a bit easier, we didn't account for the full mill. We only account for the top of the mill, even though there's still particles here in DEM, and there's fluid here, and there's the DPM particles injected exactly at this interface between the slurry, the classification zone, and the grinding zone. So what we did is a number of simulations, as you can see here, and as we said, it ran for quite a while. As you can see here, those particles in blue are essentially the tracers that we wanted to see where they went. Did they really overflow the mill, or they drop back? In the ratio between the particles that are really overflowing or dropping back and those are being fed is what we call here the partition, or the probability of returning to the grinding zone. And for each of these cases that we look at different flow rates and different percent solids, we build the partition curve, which is basically a classifier. So it basically shows what? That for coarse particles, the likelihood of them dropping back to the grinding charge is fairly high, because of course they're very coarse particles, high settling velocities. And for very fine particles, there is like a bypass here showing that even very fine particles have a good chance of leaving the mill, dropping back to the grinding charge. Of course, there will be some overgrinding here, but this is really typical of these mills. On the other hand, there is a slight change in cut size as a function of variables that we use, tip speed, percent solids, and so on. Just to show one result here, comparing the effect of percent solids, we can see very clearly that the percent solids does have an important effect on the classification. For instance, a lower percent solids here, more dilute slurry, would really reduce the cut size, uh, dropping really quite a lot the classification curve. Whereas using higher percent solids, you increase quite dramatically the D50 or the cut size. What would be the implication in grinding of this? Well, for that particular muse used by Alex, the outcome was that, yes, yeah, if we model the mill with classification or without, the size distribution would essentially not change. The reason is quite obvious because in those tests, he used a feed which is almost everything below 100, 200 microns. And you can see here that basically below 200 microns, almost no difference here in the partition curves. Basically, everything goes overflows, nothing drops back. But the nice thing is that, of course, we have a tool now that we can potentially use for assessing for real grinding mills, for relatively coarser particles, how that classification zone could potentially influence size reduction. Now going to the grinding zone description, we essentially, of course, as it involves coupling of PEM and CFD, we wanted to describe very accurately what's going on here. And because of the motion of the steerer, we needed to have a variable uh, uh, mesh here that moves the whole system. And after some effort, we got into this meshing. And what now we wanted to see how the environment changes from the bottom to the top as far as grinding ability from the bottom 0 to 800 millimeters. So basically what we did is first really account for the fact that we have a stress rheology variation as a function of particle size. That was accounted for in the latest version of the model. This is data for limestone. And what we have seen here is that the average ball velocity, as we expect, is fairly low in the bottom of the mill, which is here, as you can see, the very cold colors. And as you move from bottom to top, the velocities increase. So more or less suggesting that there are three zones as far as grinding intensity, higher in the top, lower velocities in the bottom. And also what we could see, as other people have seen in the past, is that obviously near in the inner part of the screw, the grinding media are moving up, whereas in the outer parts of the mill, the grinding media are moving down. So more or less in a convection type of behavior for the grinding media. Of course, the slurry is moving through the pores between the grinding media. So even now going further to this particular mill and describing what is going on, we decouple this classification zone to the grinding using three mixers in series because we acknowledge that there's basically three different zones that we could recognize: the bottom, the middle, and the top. And the result is that we have those collision distributions. The upper one ended up actually being on average lower frequency, lower energies involved, whereas the middle and lower were relatively slightly higher, as you described like this. So we all now have all the building blocks for prediction using the model. So now we went to the fitting part. So in this case, we didn't have breakage characteristics of the limestone. So we needed to use the simulation to backfit some of the breakage parameters. We used the dynamic version of the model. So remember that when the mill started operation, we assumed that it was filled with slurry with the feed size distribution. So in very short, if you look at the discharge of the mill at very short times, 2 minutes, 5 minutes, 10 minutes, it's still relatively coarse. So it really took about 1 hour, as you can see here, for the mill to reach steady state conditions. And essentially, as this graph is showing, so probably in 30 minutes, it was already close to that. So those predictions now we compare to the measurements, which is the symbols here. And those were the basis for the model fitting. So pretty much the same curves we could predict. But the nice thing is that now we don't change anything in the model and do all the remaining simulations under the same conditions. So for instance, one thing we could do is not only predict this first pass, which is basically what was done there, but also simulate the second pass, the third pass, and the fourth pass. And you can see here very nicely that the size distributions that are predicted are very close agreement to the measurements, basically quite clearly extrapolating the model under these cases. And now we wanted to see the ability of the model to really predict other conditions. So from the base case of 100 RPM, here, which is the red that we use for model fitting, as I showed before, we could actually predict what happens with lower velocities like 50 RPM and higher velocities like 150. 50 RPM, very good agreement. 150, the model is too optimistic. It's thinking it's going to grind finer than it actually did, but still fairly good predictions considering that there's no model fitting. And when we look at other combinations of grinding media volumes here, 120 kilos of material, 80 kilos, and so on, a combination of speeds, you can see also that the model was really good agreement with the data. So giving us quite a lot of confidence that the model will be able to deal with other conditions. So comes to the conclusions that the vertical stirred mills, in my opinion, are ideal combination devices to study via these advanced tool models, just because too many of them and too many designs, too many variables for us to explore through experimentation. A mechanistic model has been originally proposed for tumbling mills, and we have done that a number of years ago, but we acknowledge that this model needed to be improved to deal with vertical stirred mills. We do this by modifying, adapting, especially including other tools like CFD and DPM to describe what happens inside the slurry and with the classification zone. We are quite confident that we have been able to demonstrate the validity of the model in batch grinding, and we have been able to describe now continuous milling through, for instance, the classification zone has been described using DPM and CFD, but we have seen that for those conditions that were studied in that PhD thesis, they were not likely to be important and probably only relevant for very coarse grinding. When in that case, it's not likely that even stirred milling would be fantastically more attractive than ball milling. And mechanistic mill model predictions were in very good agreement with experiments at a pilot scale, as I just showed you. What are we busy right now? So we're working to improve and validate the model for internal DX classification that really was not calibrated with real measurements. We're doing this in the lab. We're now busy starting to work with the VTM 100, 1500 from Anglo to be able to apply this model to a real large scale mill that's for grinding iron ore. And we're just starting to look at horizontal stirred mills, looking forward to also see the potential of using our approach. So this really puts us to the conclusion of the work. Of course, Malcolm, for facilitating getting the data from Hassan's work, his protege at the time, and Alex also getting the data from his PhD thesis now 25 years ago. Very nice contribution from them, of course, and from all the lab, the team from Valley who has been really supporting some of this work, and of course the whole group from the lab here in our party last year. So thank you very much for your attention as well.
Thank you, Professor, for the very interesting presentation. And so we have some time for questions here. So feel free to open your mic, ask the questions, or also type in the chat that I can ask Marcelo the question.
Yes, I acknowledge it was a lot of information for for 35 minutes or so, but you can definitely, if you're interested, get in touch with me or really look at some of the papers. I think
Okay,
Malcolm
well,
is up top, right? Hey, Tony.
I think my microphone is now working,
Oh,
and
Hello.
it's really fascinating work, and so ahead of the general field. And the interesting thing is and I remember you doing that data on the original Maruf work, is that you could use normal with some fraction of shear. Now, in the industry, the stirred mills are spoken as they've been attrition milling or abrasion milling. And your work shows that you do perpendicular breakage for testing, you put that in the model, and it's 90% crushing impact breakage. Maybe you want to comment on that factor that's come out.
yes, absolutely, Marco. I think that's I thought of touching that, but it was a long presentation, but it is exactly on it. I think even though, of course, we do acknowledge that in a stirred mill, there's plenty more shear, and that shear has to be really accounted for us to be able to predict the outcome. In the end of the day, the responsive material under shear conditions and under normal conditions for most ores that we know, typical brittle materials are quite related to each other. So it gives us the opportunity to basically be able to say that, yes, that shear is contributing to breakage, but we still are able to understand that impact in the end of the day is what really results from breakage, because from the collisions that happen inside the mill. So it really shows that we can move around from different mill types quite well without really having to reinvent the wheel, I suppose. Even though, of course, there's a lot of nice potential of understanding further how particles respond to shear and impact. But our predictions basically show that I think we're doing well, understanding that most of the outcomes come from the normal impact. I think Arno's group has come to the same conclusions from their approaches as well for horizontal stirred mills.
Yeah, that's great. Thanks, Marcelo.
I think Tony has had his hands up, wasn't it?
I think so.
Yes, I did. Thank you, Prof. And I'm very sorry I joined very late, and I just had to sort of acknowledge it and the fact that you invited us all the time, and to actually, I'll contact you afterwards and get updated with it, especially in recognition that Tamara is now ready to continue with the old processing models from the old P9. So we will interact and then we can have some good discussions following. Thank you. And sorry about that. Sorry for being so late.
Okay, no, thanks, Tony. Very, very welcome on that. Yeah, I think I have to say that this work we have been doing on the background, which is self-funded as most of the time and using basically as a PhD student work. We thought it was a good opportunity here to show to the larger group that we're very confident that things are holding water. And as I said, even though we work with ball mills, we have to understand that ball mills, we understand plenty about them, and there's not a whole lot you can do different in ball milling, but you can do plenty in vertical stirred milling. There's so many variables that you can change in design, operating. That's why we ended up investing a lot on this.
Any other questions from the audience? I think Anderson. Please, Anderson.
Yes, can you hear me?
Yes, please go ahead.
Yeah, sorry, so there is noise in the background. I'm in the laboratory now. Thank you, Professor, for the nice presentation. And as you know, I've been following the work for quite some time now, and it's good to see how far you went. I have a question more on the, let's say, on the actual model side. Is as you keep increasing the passage numbers and the particles start getting down and down and down, you start to see more increase in viscosity. And okay, maybe not so much on the mining industry, but in other applications. But how do you think you could implement this change in viscosity and without having to redo the CFD for every passage?
Yeah, I think that's a very good question. And that's one that we are facing right now. I just showed there very briefly that we are starting to account for the increasing viscosity as you reduce size. And we have seen the need to do that to be able to prevent the model from over predicting size reduction, because in the previous version we didn't account for that effect, and we very much over predicted fineness, even in a mining type of application. But you're right, what we are doing right now is something which is kind of a pain, but that's our approach right now, which is to run the CFD simulation with a size that is a feed size that is coming into the mill. And then we finalize the simulation of CFD, run the population balance model, and now feed back the outcome from the population balance model to iterate with the CFD. So it goes even worse from what you're talking to be. Right now, we're doing an iterative approach that requires CFD simulation, DM, with then repeating population balance and so on. With 2 iterations, it already converges. But it really means that every time we are needing to run CFD simulations. So we are still, you see, it's still in the proof of concept thing. We believe that we still need to demonstrate the value of the tool to then find better ways to really optimize all the tools. Because it's right now, the population balance is not even coupled with the CFD. It's actually done as one-way coupling. We think that now we are so confident that we are starting to see how we can really improve the efficiency. Right now, it's not something that it is done in a minute. It really requires days to do that. But I guess that's the future. But we believe we can really account for this increase in viscosity and the effect in grinding very well with rheology, proper rheology modeling.
Well, following the queue, we have also Andre here, the second one. Please, Andre.
Thanks for a very interesting presentation. I just want to get back to the I think Malcolm alluded to the breakage mechanisms in stirred mills, and seems like it's a quite tricky one to understand for a stirred mill. We came a long way since describing the breakage in a tumbling mill from impact and abrasion and attrition, and that could basically describe almost everything, and perhaps compressed bed breakage was added later, and you're not talking about bed breakage in this case, but you kind of come back and say a lot of it can be described by the impact normal loading kind of feature. And in the good old, in my mind, often we combine the abrasion and attrition in one group. But I think, abrasion obviously on its own has a very different appearance function, but from impact breakage. And now you're saying the shear breakage has a very similar appearance function, which kind of tells me that perhaps the attrition side of it, because this is mostly attrition, it's not obviously abrasion. Am I right to understand that the attrition on its own is perhaps a very similar appearance function to the impact?
Yeah. No, I think that's a very good point. So really going a bit more into this, as you said, yes. So the idea is that the attrition effect, which is you really have to have a high normal load with, in addition to a shear, to be able to break particles effectively, which is in the end the attrition. Attrition exactly looks pretty much like the same appearance function, as you could say, the way the particle breaks as the impact. And as long as you add this proper effect of shear. On the other hand, our model still accounts for the fact that when you just barely have those grinding media move against each other with a little bit of normal, not much, there is still a chance that the particle may have some surface mass loss, as there is in the very low normal impact. And this is, of course, a very different appearance function, different way the particle debris appears. And this is all accounted for in the model. So that's the key thing. So I'd say there is this surface breakage. There is a little bit of relevance, and there's not a whole lot of it contributing to the finds in this mill, but the attrition can pretty much be lumped into the impact as far as the breakage, the way the particles appear in the product. So pretty much along the lines that you just mentioned. And the model is accounting for that as long as you account properly for this shear. We don't understand yet how much and why, but we have seen that the percent solids has an influence on that proportion of the shear that comes into contributing in the normal to the normal energy loss.
I have a question. We
just
that...
Michel,
yes.
There is a queue here with some other questions.
Sorry.
No worries. But I think the next one is Aubrey.
Marcelo, thank you very much for that nice presentation as usual, and a very worthwhile topic to talk about. The question I wanted to ask, it's twofold. The first one is, you showed that the breakage rates, if you look at the solids concentration, at the fine end, the higher solids concentration, the rates are diminished, but they rise as you go to the coarse end. Do you think that is an influence of packing when you go to the coarse end as compared to the fine end, or then the second part to that question is, you looked at when you showed the motion in the system, it appears that at the top the packing is very different to the one at the bottom. What could be the driver for that? And the reason for my question is, most of the people that run these mills recommend running at much lower solids concentration than what you tested in the upper regime. And what would be the influence if you go horizontal? Because I suspect it will be more aggressive there. Thank you.
Oh boy. All right, that's $1 million question there. I think let's say that what we have seen in our simulations and obviously in Hassan's work is that these rates and the percent solids are really changing in a not obvious manner, because if you really use traditional population balance models, it's very hard to predict that. I think your point is well taken. I think it can be related definitely to this packing effect, because remember that the model is sensitive to bad configuration, because if you have more particles participating in every collision, there is split in energy between the particles. Because if you have low solid concentration, you sometimes are nipping in almost individual particles there. And where you actually have higher concentration, you have a bed of particles that are really sharing that collision. And so I think these points are really worthwhile that you're raising. And I think it really fits to the idea that, well, how do these compare vertical and horizontal? Under these extreme conditions, very differently, I'd say. And I think really very good point to open the black box. So I think you brought some very good provocations. And what we have seen, we're very struggling to even believe the results that we are getting. But I think they're very consistent with what we've seen in different mills. I think you may have just got the idea right now how to approach it. Thanks very much, Aubrey.
Oh, still have time here for two short questions. I think we have Robert and Shujat in the queue. Please, Robert.
Hey, thank you. It was a very great presentation. Thank you. One of the things I saw was that you use for the simulation really big particles, really big beads. In the industrial, we are using smaller beads, up to 100 micron or something. Usually you can't simulate such amount of beads because too small, too much, too computational costly. We are using coarse graining to simulate it, and with coarse graining, we are simulating several beats as one and make the changes in the fluid terms, so bigger surface and so on. What would be the impact of this coarse graining on your model?
No, I think that's a very good question, and bear in mind that yes, I think DEM simulation and especially coupled to CFD, the number of elements can be quite tricky and have a major impact. So remember that we started from the mining application, from bone milling. No wonder, because it's really coarse grinding media, very easy to simulate. And we started even using 25 millimeter balls like Hassan's work, 20 millimeter. It's pretty cup of tea to do that. Yes, right now we're simulating 2 millimeter balls, and we're already seeing that it's a limit that we can even do as far as reasonable simulation. I think you see, just our approach right now is really to prove the concept, is to say that yes, if all conditions are certain, if we know exactly what's going on in the mill, can we predict the product? I think the coarse graining is exactly what is necessary here. As you said, there is potential to that. One has to just be careful not to lose sight of the frequency and the magnitude of collisions, that we have to really deal with that properly in order to really not create something that is unrealistic. So the short answer to you, we have not done that, just because we have right now laid back on the comfort zone, which is how the model works if it's all resolved as far as particle. But I think coarse graining as collision energy and frequency can be done, but it really increases the level of uncertainty. And we hope to be doing this very soon, and hopefully with you guys. But at least with knowing that the model already holds water under optimal conditions is exactly what we have done. So
thank you.
I guess that's the best answer right now.
So, Shujat, you have a question, please?
Yeah, sure. Thanks, Marcelo. Great talk. My question, just out of curiosity, I wanted to know if the modeling approach that you got has any dimension, includes or takes into consideration any dimensional parameters, because what I saw was when you were changing the mill width and dead zone was also changing, and so the breakage rate. So, want to comment on that?
So if you can say that again. So what dimensional ratio?
Yeah, any dimensional parameters of the mill?
Yeah. So, but the nice thing about DEM and these tools is that we're basically designing the mill exactly as we want, as ball sizes, diameters, screw characteristics, and so on. Yes, I think what you're alluding to is what where we're looking forward to in the near future, which is, well, now we are already seeing some very well developed relationships, some dimensional relationships like that. So the same thing we saw from ratios of screw to diameter for that mill, it will probably hold for other mill dimensions and other diameters, because I think these things tend to be relatively robust. But bear in mind that ball size will be important. So we haven't done that yet for this because we haven't run so many different conditions. But this is, I'd say, it's the vision for the future. Is not to have to do DEM simulations for everything all the time, but to be able to understand these relationships. So use simulation to understand these dimensionless numbers to be able to include in future designs. So, but right now we are pretty much simulating case by case.
Sure. Great. Thank you.
Okay, thanks, Sally.
Thank you, Marcelo. And we had here in the queue Michel, but not sure.
Yeah. Yes. Oh, sorry.
Then Holger. Our two last questions.
Okay, so it seems that we are associated with normal force to impact, and for me, impact, you need that space between the balls. And when you take a look at those tower or vertimills, it seems that those steel balls are compacted each other, because the weight of steel is pretty high. Is it possible that those normal force is more compression or something like that? And can you investigate if that normal force, I mean, that normal force is increasing as you go in depth? Because that might help to answer that source of that force, right?
No, absolutely. No, yes, Michael, thanks. Yes, indeed. I think what happens is that you can see that the model on DEM in this case, it's quite clear that except for the case that you have the very bottom of the mill, that almost nothing is going on there, almost grinding media stationary. The At the depths of the mill, of course, the hydrostatic load on the particles creates quite a bit more pressure between grinding media. So the normal and the collision distribution there is quite obviously much higher for the bottom grinding media, and this is certainly associated to the higher normal components of the impacts. But also the shear, as we have seen as well. As we go further to the top, even though the frequencies are fairly high of the grinding media colliding, but their energy is not as high because some of them are almost free in touch with the interface. So this is certainly is what we call the gravity-induced grinding vertical stirred mills, which has really a benefit of really having some of that effect, not the fully fluidized version. So this can all be certainly investigated using these tools for sure.
Okay, thank you.
It's Holger.
Yeah, welcome. Marcelo, thanks a lot for the interesting presentation. Unfortunately, I came in early late. I have one question. Are you aware about any ways to look into the mill for verifying what really happens inside these stirred mills? I mean, we know the input data of the material, the output data, we know the energy consumed and the stirrer torque, maybe the energy. But any idea how to have to verify really what happens in the mill, particularly if you come to the geometry or so of the stirrer? That would be quite interesting.
Yeah, thanks, Holger. Definitely a very good question. Yes, I think definitely it's not very comfortable for us to just relate looking at outcomes and trying to fit that. Of course, what puts our minds at ease is the fact that when you change operating conditions and the same predictions appear as far as the model being robust, it tells us that our assumptions are not too bad. Yes, but on the other hand, I think I definitely think that we are looking right now at we're doing in our own pilot mill here to be able to do this tests where we trace particles to be able to really measure that classification effect that we predicted. On the other hand, I think there's PEPT, positron emission particle tracking, that is pretty nice into that, just to demonstrate. People have used that, Aubrey's group and so on, to show the convection effect of the grinding media. So I think now there's definitely a lot of interest, in my opinion, to be able to look more experimentation in depth, to be able to understand if the assumptions we make are right. Because in my experience, many years now, I'd say that there's the balance between the modeling and the experimental part, isn't it? Sometimes the experimental part is fantastic. People really do fantastic things, but we have no use for that information because we don't understand. But sometimes there's the opposite, which is there's a lot of fantastic tools and make a lot of assumptions, but we are not so sure if they are really backed up by reality. In my opinion, right now, the modeling has really pushed forward quite a lot. I think our group and Paul Cleary's group and Aubrey and the team. But I think the experimental part is lacking to show really exactly the minor scale influences. So it really requires us to go back and try to do better experiments. We're trying to do some here to validate some of them. But I fully agree that the model is almost going too far and requiring some in-depth measurements to be able to demonstrate that we're doing well. So good point. I think a lot of opportunities. PEPT is one of them, tracing particles and so on, creative things. But in order to be able to put us at ease when we look at industrial systems, because of course what we wanted to be able to do shortly is to potentially even design a new mill and say that there's going to be a better mill than the others. But in order to be able to do that, we have to be pretty confident, and it goes to the experimentation beyond size distributions and power.
Okay, thanks.
Thanks, Holger.
Thank you, Marcelo. Very nice presentation. a lot of good discussions here, a bit over time, but with good discussions and good talk.
Indeed.
So thank you very much for
Thank you
all
very
of you
much,
attending
everyone.
and being here now. So
Yes.
see you in a month's time.
Okay. See you guys.
Thanks,
Thank you
everyone.
very much.
Thanks, Marcelo.
Thank you.
Thanks for
Yes.
joining us. A good crowd today.
Yeah,
See you.
Cheers.
they're good
Yes.
colors.
Thank you, everyone. Very much.
Thank you so much.
Bye,
Cheers.
Carlos.